We have used, in the past two clips, a standard ruler, the size of the horizon at decoupling, or 1 over root 3 times that, to make measurements of the universe. And we have managed both to make measurements of the parameters at 380,000 years of age at last scattering, and through the baryon acoustic oscillations and their leftovers in the distribution of galaxies and clouds at all values of z. Wouldn't it be pleasant to make another measurement? What is another way of measuring distances into the universe, or parameterizing the distance redshift relation? Well, we can measure the redshift of anything. If we could measure the distance to it, we'd be in business. We use standard rulers. Now we can use a standard candle. We've made a big deal about objects whose luminosity is known and which can be seen deep into the universe. They're called type 1a supernovae, like the one that recently exploded in M82. And type 1a supernovae, we know, are, after one makes a correction for the length of time that it takes their luminosity to decay, very predictably a standard candle. Therefore, if we measure their brightness, we can figure out their luminosity distance. If we measure their redshift, we then have their coordinate distance, and we have distance and redshift. We can directly measure the distance-luminosity relation. This was clear in the late 80s, and in the early 90s, two groups set out to make this measurement and to measure the deviations from the linear distance redshift relation. What they were measuring, in fact, is the deceleration parameter. We talked about the fact that the deviation from a constant h is measured by the time derivative of h. This shows up as the deceleration parameter in the Friedmann equations, and these two groups separately set out to measure the deceleration parameter. There were several technical obstacles that had to be overcome. One, astronomical, had to do with the fact that when a supernova is very far away, its light is redshifted. This means that when you're measuring the luminosity or the brightness with a visible light detector, you're measuring actually a different part of the spectrum. Some of the visible light you're detecting was emitted as ultraviolet. This is known as the K correction. It requires that you adjust the observed luminosity for the fact that you're observing a different part of the spectrum as a function of z. But we know something about the spectrum of a supernova from nearby supernovae, so we can figure out that K correction. The other was a logistical problem. To make these observations, one needed time on large telescopes to observe large swaths of the sky and see if a new star showed up in some distant galaxy that might possibly be a supernova. The problem is that time on these telescopes is at a premium, and the issue was how to arrange for time on these telescopes observing where most regions of the sky on most given nights will not allow you to observe a supernova. Both of these problems were solved by two separate groups, and they both set out to measure the deceleration parameter. They both were measuring the distance redshift relationship and looking for a small deviation indicating that expansion was slowing down. Remember that what we expect if expansion is slowing down is that at large distances the observed redshifts would be larger than they would be based on the distance redshift, on the Hubble linear relation. In other words, we expect the distance redshift curve to turn over to the right. And what both groups independently discovered, to their astonishment, is that the deceleration parameter is negative. In other words, they found that the curve deviates to the left or up from the linear relation. Now you see here their data, you see that it's not with the supernovae at redshifts below 1, quite difficult to discern. There's a noisy signal because there are ambiguities in the precision luminosity calculations and so on. But if you look over here closely at this figure, you will see that the decelerating solution, that is a dust-dominated universe without vacuum energy, is excluded by the error bars on this data. What they were measuring is that the expansion of our universe is accelerating. From our understanding of cosmology, this means we have a non-zero cosmological term, because that is the only term that contributes with a negative sign to the or a positive sign to the deceleration equation, a negative sign to Q. And so they are directly measuring the existence of a cosmological term. If you want, you can, these days we have measurements at even larger values of the redshift, and you can see that we observe nearby supernovae. For nearby supernovae, we observe the linear expansion, the linear approximation, and then at larger distances, we observe that the universe is accelerating, and in fact, the most distant supernovae discovered actually begin to show us the downward trend. In other words, they show us that in the past, expansion was decelerating. This is supernovae so distant that they are observed before the turnover point from dust-dominated to cosmological constant-dominated universe. So what the Supernova 1a surveys gave us as an amazing technical feat, but also in terms of data, is they give us a direct observation of the distance redshift relationship, and as the first approximation, they measured a negative deceleration parameter, indicating that currently our universe is accelerating its expansion. And what's left to us now in the next clip is to assemble all of the data that has been collected by these various observational enterprises that we discussed, and see how we derive from this the data for our universe that I claimed we know.